Hello everyone, myself Dr. Feroza Demirajkar, and today we will see a 8051 assembly language program to convert a given number from gray to binary. Gray code is a type of binary numeral system where two successive values differ in only one bit, and it is often used in error correction and digital systems to prevent spurious outputs during the transition of the states. Suppose we have a binary and a gray code number. When we want to convert a gray code number to binary, the MSBs of both the numbers will be same. That is, if G0 and B0 are the MSBs of the binary of the gray and the binary numbers, then G0 will be equal to B0, and to find the subsequent bits, this formula is used. That is, to find out the current binary bit, the previous binary bit, it is XORed with the current gray code bit. So we will see this with the help of an example. Suppose I have taken the gray code as G is equal to 1011. The first step will be we have to copy the first gray code bit as it is from the binary bit or the binary number, that is B0 will be equal to G0, that is equal to 1. So this is 1. To compute the second binary bit, that is B1, we have to take B0 and G1, that is previous binary bit should be XORed with the current gray code bit. So now the current gray code bit is 0 and the previous binary bit is 1. Okay, so 1 is XORed with 0, we get 1. To compute the third binary bit, that is B2, you have to XOR this with B1 and G of 2. So B of 1, that is the previous binary bit, is what? It is 1. And the current gray code bit is 1 here. So 1 XORed with 1 is 0. To compute the fourth binary bit, you have to take again the previous binary bit and the current gray code bit. Previous binary bit is 0. So we have placed a 0 here. And the current gray code bit is 1. So 1. 0 XORed with 1 is 1. We get B is equal to 1, 1, 0, 1. So here we have 1, 1, 0, 1. So here this figure shows how the gray code is converted to binary code. Suppose you have 1, 1, 0, 1, 0, 1 as the gray code. Now you have copied the most significant bit, that is 1 as it is. Now this is XORed with the next bit of the gray code. Okay. So 1 XORed with 1, we get 0. Now this bit, okay, suppose we want this bit. How we'll do it? We'll take the previous binary bit, current gray code bit, we will XOR it, we will get 0. To get the next bit, we'll take the previous binary bit, we'll XOR it with current gray code bit, we'll get 1. Again here, to get this, we'll take previous binary bit, we'll XOR it with the current gray code bit, we'll get 1. Similarly, here we'll get a 0. So here you have another figure. You can go through this also. These are the, this is the gray code table. This has been, this is there in the binary to gray program also. I have put there also. You can refer there also. Now this is the program logic. What you have to do, you have to load a value from the memory address. Suppose we are taking 30H and this value, it has to be loaded into A. We are taking the value from a memory address into the accumulator. After that, we have to perform a series of 7 circular write shifts on A, that is on the accumulator. For each rotation, what we have to do is we have to update B by XORing it with the current value of A. After completing the 7 iterations, we have to store the final result in B at the next memory location, that is 31H. Then we have to stop the program, that is we have to halt the program. Now we'll see the program. This is the program to convert a gray code number to the binary number. The first step is the initialization. So here what we'll do is, again we'll take org0000h, that is the starting address of the program. After that we have move r0 comma hash 30h. This instruction is used to initialize the register r0 with the address 30h, that is source address in the memory. Next is move r2 comma hash 07h. Here we are initializing the loop counter r2 with 7, indicating that there are 7 iterations. So here r0 is used as a pointer to read from and write to the memory, and r2 is the loop counter for 7 iterations corresponding to a 7-bit circular write rotation. Okay. Then next is we have to transfer the data now. Next instruction is move a comma at r0. Here we have to load the value at memory location r0. r0 is what? It is 30h into the accumulator a. After that, next instruction is move b comma a. So here we'll copy the value from the accumulator to the register b. Okay. So the value stored at memory address 30h, it is loaded into the accumulator A, and this value it is duplicated into the register B for further processing. Next is you have a loop here. Okay. So up is the label. Now we have to perform a rotate write with carry. So RRC is the instruction, RRC A is the instruction which we are using. This will rotate the accumulator A right through the carry flag C. Then the next instruction is CLR C. Here the carry flag is being cleared. The next instruction is XRL B comma A. We have to perform an XOR operation between B and A, and we have to store the result in B. Okay, we have to store the result in B. Next comes DJ NZ R2 comma up. So here we have to decrement the counter. Okay, that is decrement R2, and if it's not 0, then you have to repeat the loop. Okay, so here RRC A, it will rotate the bits of A one position to the right, and the least significant bit it is moved into the carry flag C, and the carry flag is shifted into the most significant bit. This CLRC, this will clear the carry flag and it will set C to 0. Okay. And here XRL B comma A, it will XOR the contents of B and A, and it will update B with the result. So after that, next instruction is what? It is increment R0, INC R0. This will increment R0 to point to the next memory address. The next instruction is move at R0 comma B. Earlier the address was 30h. Now it has incremented to 31h, where we will store our result. So here the final result will be stored into the memory location pointed by R0, that is 31h. Then we will stop the loop. We will enter an infinite loop to halt the program. So this is the program. Here we'll give the input as 6 at 30th location, and we have to get the output as 4 at 31st location. These are some of the applications of the gray code. Applications of gray code conversion. First is rotatory encoders. So here the gray code, it will minimize the errors in position detection. The second is digital communication. The gray codes will be used in error correction and noise resistant data transmission. And the third is circuit design. That is, it will reduce the likelihood of glitches in digital circuits. Now we will see the execution of the program. I will copy the program from here. So double click on this icon of the Keel software, maximize it, go to the project, new MuVision project. I'll take the previously created project. Yes. Search for the device, microchip. Click on the plus symbol and search for 8089 C51. Okay. So 8089 C51 is here. Now click on OK and click on No. Click on new file and new. Then paste your program here, or you can type your program here, then save it. So it is which program? Gray to binary. So it is, I'll write it as G to B, and I have to save it with .asm instruction. So save. Next, click on yes. Now go on to the target, click on the plus symbol, you will get source group 1. Right click on the source group 1, click on add existing files to group source group 1. Now type your program name. It was G2B, that is gray to binary .asm, add, close. So now go to project, build the target. You can see here there are 0 errors and 0 warnings. Now go to debug, click on start or stop debug session, click on OK. Now you need only one memory window, so memory 1 is there. Our location is 30H, so I:30H, enter. At 30H we will give our input, so I'll write here, I'll type here 6. Now run the program. So you are getting 4. Okay, this is the gray code and this is the binary number. So this is how the program works. I hope you understood this. Thank you.